Okay, good morning, good afternoon, and maybe good evening, ladies and gentlemen. And I'd like to welcome you all to the second day of this workshop, Fundamentals of Nodal Analysis and Basics of Two-Phase Flow. If you have attended our first session, we spoke about the basics of nodal analysis and what are the applications of nodal analysis, how we can use nodal analysis to determine several, I would say, well production conditions by evaluating the effect of fluid phase ratio, for example, changing of water cut, changing of GOR, which of course will change the density. And then we clarified how we distinguish between the inflow parameters and the outflow parameters, okay? Today, we will be focusing mainly on the inflow and how we calculate the IPR curve, or how we generate the IPR curve by selecting few of the famous IPR methods. Of course, if you search the literature today, you'll find a lot of more and different IPR methods that are developed for certain completions. And until today, you'll probably find, from now and then, new changes to an IPR method. For example, for let's say multilaterals, or for certain completions, certain even hydraulic fracturing and so on, tight reservoirs. So each completion and reservoir conditions might have a different IPR methods. So today's session is not really to explore all these IPR methods. It is just to give you a sense of the different IPR methods. And I'd like to emphasize the fact that today we are going to throw several exercises. All right. These exercises are going to be available in the recording afterwards. And then I recommend that you use Excel, for example, if you want. Of course, Excel is the best to actually generate these IPR methods. And these exercises are going to be, this is just probably a cheating now. These exercises are the ones that I'm going to ask you on the quiz on day 3. So end of day 3, we are going to have a quiz, right? And the exercises that I'm going to show today will be exactly asked on the quiz. So you better take these exercises on your own and do them. I mean, each exercise will probably take you 5-10 minutes, maybe 20 minutes. But this is very useful, and you will feel confident that you are actually generating your IPR methods yourself, okay? So today, this is the agenda. We are going to show these different methods. We'll be talking about the most, I would say, famous one, the productivity index. Then we are going to talk about Vogel method and standing method. Strange thing is that standing method is not, you don't see them available in the famous production performance software such as PipeSim or Prosper, and the reason is because the standing method is nothing but, you will see, it's a modification of Vogel method, and even Vogel method itself is only applicable in certain conditions, which is saturated reservoir. But the rest you find them in all these similar software. Okay, so let's talk about the IPR methods. But before that, we need to keep in mind that the IPR methods, the IPR curve can change due to several parameters. Okay, meaning when I say that can change, meaning the IPR curve, when you generate it, these parameters will affect how the flow and bottom hole pressure will be calculated. Or if you specify the flow and bottom hole pressure, calculate the rate, then the rate will be affected, okay? Number one, of course, is the fluid properties. And here I'm showing you if you recall, we showed Darcy IPR last time, I remember, okay? So for Darcy IPR, this is before integration, but what I'm trying to say is here, if you can see that this J method or the PI method using Darcy method is actually directly proportional to K, permeability, mu, the viscosity, and B, which is the formation volume factor, okay? So these parameters, the fluid properties, okay, the fluid properties actually are going to change PI. They are going to affect the IPR calculation. And this applies really to everything, right? However, when we use the PI method by using testing, bottom hole testing, we are actually measuring only the flow and bottom hole pressure, and we construct the IPR curve based on that. But and this is because we're not using the analytical method, we are using just the numerical method. So the difference between analytical and numerical is based on testing, right? Whereas analytical is based on the fluid properties or the reservoir and fluid properties. So for example, this form here is an analytical form that takes into consideration the permeability, viscosity, and formation volume factor, okay? So, which means that, and you will notice that this is KO, BO, mu O, and BO, which is basically oil, right? Now, anybody would think that, and this is of course obvious, by changing the fluid phase ratio, meaning if I have water, let's say 50% of the produced hydrocarbon is water, then I need to adjust this term, right? And that's why we have the relative permeability curve that will be taken into consideration. Meaning that what is the relative permeability? It's the permeability of the certain phase to move in the rock. Okay. So let's look into this curve here. So for example, if the water saturation is increasing on this x-axis, in the beginning it is 0, meaning it's mainly oil, right? So that means the relative permeability to oil is the maximum, okay? And then as the water saturation increases, the relative permeability of oil will start to drop. And at one point, the relative permeability of water will start to increase until, well, the whole fluid becomes water, and then the relative permeability of oil will drop to 0. What does this mean? It means that because the mobility of water is much stronger than oil, right? That's why we need always to avoid producing water, because once the water approaches the completion, we call it water encroachment, right? Then we will expect that more water will be invited, because water can move easily to the completion. Water can, because it has its much lower viscosity compared with oil, it can easily move in the rock. Okay, so this will be taken into consideration when we calculate the PI. Similarly, the viscosity. Okay, now the viscosity also changes with temperature, right? So for areas where we have heavy oil meaning of course high density, but this will also affect the viscosity. How can we reduce the viscosity and make the oil more mobile? Well, by heating it. And that's why we inject steam, right? So we inject steam to heat the reservoir up, and then this will reduce the viscosity, yes, of oil, and this will allow oil to move easily to the completion. And also the formation volume factor, the volume, okay, the relative volume of oil, right, due to compression and so on, all that affects the IPR calculation. Okay, so fluid properties, that's the first one, and that's why normally we need to enter correct fluid properties if we are using the analytical methods. You'll notice that, for example, if you're using productivity index, normally these properties will not affect the PI because you just entered one number. But if you use, for example, a horizontal IPR, or you're using a Darcy method or any analytical methods, then you will notice that the IPR will change based on the fluid properties. Number two is the drawdown itself. So for example, depending now where you are, okay, and how much you're producing, you will notice that the drawdown will start to change. What does that mean? Look into, for example, this curve here, the red line, okay? So we're assuming that, remember last time we said it was found that by Ln 0.472 RE, which is the extent of the reservoir or the drainage area or the drainage boundary limit, right? Considering a circular drainage box or cylinder. At this point, we assume that the reservoir pressure, the flow bottom pressure equals the reservoir pressure. And then having a Ln a logarithmic scale on the distance, okay, we will see that there is a straight line between the Ln 0.47 RE until the well bore. So this is the well bore, okay? Now, this condition here is at low flow rate, all right? At low flow rate, this is the, let's say, this is the oil flow rate. This is the IPR curve, okay? We are producing here, right? So it's a low flow rate. And why do we have the flow bottom pressure above the bubble point? Well, because the drawdown is not very much very high, and hence it is a straight line. However, as you produce more at higher rate, you will find more drawdown, correct? And hence the fluid will reach the bottom, the bubble point pressure, and then we will see that there will be more pressure drop after the bubble point. Why? Because we have two phases now. We have gas and oil that are competing to enter the wellbore, and that's why we have more pressure drop. We call it two-phase skin, right? And that's why we see that we will have more drawdown, or the curve of the IPR will go down, right? And this is similar for the higher. And so as we increase the production, right, the drawdown will increase, and we will have more tendency towards producing below the bubble point, okay, in the completion, in the well, in the bottom of the well, right? And of course, the pressure depletion. Pressure depletion affects what? Affects the starting point of my IPR curve, okay? So this is again, this is Ln R, which is the radius from the wellbore, okay? This is the wellbore here. And now, as we produce more with time, let's say, for example, if we're producing from a shale reservoir, the reservoir pressure will be depleted very soon, sometimes months, sometimes weeks, okay? So unlike, the conventional reservoirs, which you can maintain the reservoir pressure, but as the reservoir depletes, as the reservoir pressure goes down, right, we will reach to a point where the starting point itself of the reservoir becomes below the bubble point. And then we call this as what? We call it the saturated reservoir, okay? The undersaturated reservoir. This is the saturated reservoir, okay? So, and this is obvious from this picture here, okay? The starting point of the reservoir pressure will affect, of course, the IPR curve shape. Now, talking about the productivity index. As I said, productivity index can be looked at from two angles. it can be measured, and we can use it to basically find the number, the productivity index. Okay. However, this number, okay, will, as we are going to see in the future, we need really to be careful whether the flow bottle pressure that we measure, is it above the bubble point or below the bubble point. However, that will come later. The productivity index is just a straight line. It's just a straight line. But then you will need to introduce what we call the Vogel correction, and I will talk about this later. So it's a straight line, and if you remember from our last session, when I showed you this IPR curve, and I said we take 2 points from the straight line, and then we said that we are going to find the slope, and the productivity is the inversion of that slope. This is basically it. So J is a productivity index, is Q at any point divided by reservoir pressure minus PWF. Okay, so how many points do I need? Well, if I know the reservoir pressure, I only need 1 point. So I will need the flow bottle pressure and the flow rate, plug it in this equation because I know the reservoir pressure, and that's it. I know my J. Okay. So, and we all know that at PWF equals 0, this is a theoretical number. So for example, as you can see here from this plot, this is 0 flow rate. So 0 flow rate is equivalent to reservoir pressure of PWF equals reservoir pressure. However, theoretically, if we manage to reduce the flow bottom pressure to 0, which is impossible, then we call it Q max, or the absolute open flow potential, right? Again, this is the theoretical number that is just used to improve or to help in constructing the IPR curve. But of course, no one can achieve that. No one can go to flow bottom pressure of 0. Okay. So this is the PI concept, right? Again, the PI concept does not take into consideration the bubble point, and that's why we need to introduce an improvement to the PI method, and that's why we need to correct it using Vogel method, which will come later, right? So again, what do I need to create my PI or to calculate my PI? Just one test point. I go and make a test where I basically open the well choke. I wait for some time until the production stabilizes. I know how much liquid rate I'm producing. Say, for example, 2,000 barrels, 1,000 barrels, 500 barrels, okay? And then I must have a downhole sensor to calculate the flow bottom pressure. And then I take this flow bottom pressure and the stabilized condition, and that's it. I should know the reservoir pressure, and then I calculate the drawdown by subtracting PWF or flow bottom pressure from the reservoir pressure. This is my drawdown, and then I divide the measured flow rate by this drawdown. I get the productivity index. Okay. Now, the productivity index represents the well inflow rate per unit drawdown. Okay, and this is, as I said, this is our IPR curve. We calculated from the straight line. Okay. Now, analytically, meaning using Darcy concept, assuming the properties, the fluid properties are not changing with the reservoir pressure. Of course, they do change, but assuming that this concept is constant, then simply we say that J equals 0.00708 KO, of course, for oil. H is the thickness of the reservoir divided by mu, the viscosity, formation volume factor, and then ln 0.472 RE divided by RW. So this is the analytical method. Okay. Now someone would use this method, right, and measure the PI and do some calculations. Okay. So for example, you know your fluid sample properties. So you know these properties, right? and you know that it's a vertical completion, using the PI, you can get H, for example, right? Because I can measure my PI, so I will equate this term with the PI value, and then I can calculate H with the height, which is the height of the reservoir, or height of the completion, or the drawdown, yeah? Oh, sorry, the drainage, height of the drainage area, okay? So this is the PI. Now, this is the general term. And as I said, if we assume that these properties are not changing with the pressure, then it will simply go back to this original one. Okay. Now, what about gas wells? So we can simply say that the gas PI, productivity index, is not inversely proportional to the pressure to the drawdown itself. It is inversely proportional to P to the square, to the power of 2 for the reservoir pressure minus the PWF. Okay, and this way also can be used to calculate J. However, when we talk about gas, there is a better method, which is, it's called the back pressure or Fitkovich method, which will need probably several points. But for example, in certain software like in PipeSim, you will find that you can enter the gas PI. Okay. Yes, I saw that someone has raised hand. I suggest please you write your questions in the chat, and then we can look into the questions later on, if you don't mind. Okay. So this is the PI. Moving on. Now, remember I said that we need to have Vogel correction. So far the most commonly used IPR method is the combination between PI and Vogel. You see always that there is Vogel correction, or it's even if you enter the PI, you'll find that it is actually automatically corrected using Vogel. Okay. So what is Vogel method actually, right? So Vogel was really smart and lucky at the same time. So he did some experiments, okay, and found an interesting phenomenon. Okay, so what he did, he created 21 theoretical reservoirs or mathematical reservoir methods by basically changing. He used Darcy basically, and he changed different parameters of fluid, viscosity, formation volume factor, drainage area size, cylinder, the drainage length, the height, etc. So he created 21 different mathematical reservoirs. Okay, and then he started to plot IPR as dimensionless P versus dimensionless rate. So what he did, let's assume that these are from the 21 reservoirs. He created 21 IPR curves. Okay, so 21 IPR curves, and then what he did, he said that, okay, for each of the reservoirs, I'm going to divide PWF by the reservoir pressure, and then I'll put it on the y-axis, and then I'm going to divide Q, which is the flow rate, at Q max, which is the absolute potential. And he found that a very interesting phenomena. He found that all the 21 reservoirs, when he plotted this interesting concept of PWF divided by P reservoir on the y-axis versus Q divided by Q max on the x-axis for the 21 mathematical reservoirs, he found that all of them are actually almost overlapping into a nice shape. Okay, and it was an excellent finding, because what he did then, he came up with a mathematical method or mathematical representation of this new curve. Okay, so this is what he did, right? Now, he came up with this famous formula. This famous formula is nothing but just a numerical fitting of this curve. On the y-axis is PWF divided by P reservoir. On the x-axis is QO divided by Qmax. And as we said, this curve here is always correct, regardless of the reservoir, right? But remember, we are saying here that this is saturated reservoir. What do we mean by saturated reservoir? The saturated reservoir is when the reservoir pressure is below the bubble point pressure. So all of it is curved, okay? And that's why you will see that this is it's to the power 2, correct? So this curve here, okay, is always, it's not linear from the beginning until the end because of this power of 2. But this is a very interesting curve because it's simple, straightforward, okay? And then it just, you can, if you know Qmax, you will be able basically to, by just knowing Qmax, that's it. You will be, and of course, P reservoir, you will be able to construct your IPR curve. And I will show you how we do that, okay? So this is our first exercise. And again, as I said in the beginning, watch out. This will come into the quiz, okay? So I'm showing you the, a question that will come in the quiz, right? So you better just learn it. So we're going to use Vogel method to calculate certain values, okay? So a well is producing from a reservoir with an average pressure of 2085 psig. So this is the average reservoir pressure, okay? If the flow rate was 2820, 2820, this is the flow rate, the measured flow rate, stochastic barrel per day, and the bottom flowing pressure was 1765 psig, knowing that the bubble point is 2100. Why did I give you this number? It's not useful here. Sorry, it's not useful here. The reason I give you this number is just to compare it with the reservoir pressure. So the reservoir pressure is below the bubble point pressure, which means that it is a saturated reservoir. So there is no, the whole curve is, the whole IPR curve is going to be curved. There won't be any linear section, okay? So now, these are the questions. Using Vogel's method, calculate the production flow rate at PWF of 0 psi. So I want you now on the chat, just by looking into this equation, I'll give you 2-3 minutes to answer this question here. How can we do that? So I want the production flow rate at PWF of 0. Can we use this equation to calculate the production flow rate at PWF of 0? I'm expecting questions on the chat. Sorry, answers on the chat. Yes. Okay. 2820 is no. 2820 is the flow rate at this flow bottom pressure. I'm talking about 0 flow bottom pressure. 1, no, it's not 1. Because you see what will happen if the flow bottom pressure is 0, this term here will be 0, right? This term will be 0. So this term and this term will go away. Then we are going to find that Q equals Q max. That's it. Correct. Now I want someone to give me a hint. How am I going to calculate? So for anybody who said Qmax, correct. So we're getting there. So the production flow rate at PWF of 0 is Qmax, and this is correct. And this is the absolute open flow. Now, how do I calculate this value? First, calculate Qmax. Good, Fuad. How do I calculate Qmax? How do I calculate? Okay, Q equals Qmax. Yeah, but how do I get Qmax? From current Q. Excellent, Fuad. Thank you. Thank you. Thank you. So this question is a trick, by the way, because the first thing that will come to mind, yeah, well, production flow rate, if PWF of 0, then I will just simply plug 0 here and then I will get it. But this will give you nothing because this will simply say Q equals Qmax. You will not be able to know how much is the flow rate. So this term here is Qmax, correct? How do I get Qmax? I have to plug in these two numbers, correct? So now I can do that simply by saying flow rate. Sorry, I need to fix this quickly. Flow rate. Okay. Can you, am I still sharing my screen or?
Yes, sir.
Okay, good. So flow rate at PWF of 0, PSIG equals Qmax, correct? So now what do? I have from the previous slide, I have the flow rate and the flow bottom pressure. So I go now and I plug the Q and PWF into this equation. So I just rearrange this equation and I found that Qmax equals what? This will come here and this whole term will go down. Equals QO divided by 1.1 minus 0.2 PWF divided by P reservoir minus 0.8 multiplied by PWF divided by P reservoir square. Rearranging and calculating, I will find this term. So this is Qmax, right? So that's it. Once I find Qmax, then this equation here can be solved to construct my IPR curve. Because I will say that Q equals Qmax times this term, and then I can assume multiple PWFs, and based on that, I can get QO. Clear? So now going back to the second question, I'll not solve this because you will need to solve it later on. I'm asking you to calculate the production flow rate at PWF of 1485. Now, how do I do that? Simple. Again, I have Qmax now, which is 10955. And then I simply, because I want the production flow rate, okay, the flow rate at this long bottom pressure. So I have Qmax, I put PWF here, and then that's it. Direct calculation, I get QO. Now, the third one is not straightforward. Why? Because it's the opposite. You will need the flow bottom pressure to produce 4,000. So the simplest is that you need to construct your IPR curve in Excel, right? Or the other way, of course, you need to solve a second order equation, which is possible, but not necessary. We don't really need to go to that detail. What we can do is that from this equation here, I have Qmax, I plug it here into this term, and then I assume multiple PWF, I calculate Q, and then I have Q versus PWF. Of course, the first point of PWF is reservoir pressure, the reservoir pressure. The last point is 0. And then I will have Q versus PWF, and then I can construct my IPR curve. And then from the curve, I can go to 4,000 straight line, and then I will find the equivalent PWF. Not very, very accurate, but good enough. Is that clear? So this is exercise number 1. You need to do your own when you have free time. It's a simple math. It's fun. So it's just for you to, move your mind a little bit, okay? Using Vogel charts. Yes, that's also possible, but this is exactly what we're saying here, right? because you see, using Vogel chart, you can also do that by simply finding this term here. You divide, you know, QO by Qmax. You'll find okay, what are we? Well, okay, we need to calculate for bottom pressure. So I divide 4,000 by Qmax. So I go to this term here, and then I go to the top, and then I go directly here, and then I find from PR I find PWF. That's also correct. Okay, but I prefer now to go to the IPR and then directly do it using the IPR. But good answer, Mohammed Mansour. Okay. Good. So this is the Vogel method. And now this is, we have done the first exercise. Now, we all know that not always the reservoir pressure is below the bubble point. It's a possibility that the reservoir pressure is above the bubble point. And that's why we call it undersaturated reservoir. In this case, we need to consider that the IPR curve must be composed of two lines. One line, straight line, from the reservoir pressure until the bubble point, which is simply the productivity index concept, and a curved line from the bubble point going down. Okay, so that's why it is a straight line for the portion of P reservoir until PWF, PWF equals PB, and Vogel from PWF equals PB until 0. Okay, and for that we need to adjust the equations a little bit. Okay, now depending on the test, depending on the flow bottom pressure and the flow rate test that we have, we need to distinguish two cases: whether our flow bottom pressure is above the bubble point pressure, or our test point itself, flow bottom pressure, is below the bubble point pressure. So if we made a test and we found that the flow bottom pressure is above the bubble point pressure, well, that's easy, because we can calculate J directly from this equation here. We can say the J, or the productivity index, equals equals the flow rate divided by the drawdown, correct? And then from J, from the productivity index, we find the flow rate at the flow bottom pressure. How we do that? QB, or the flow rate at the bubble point pressure, equals the PI, the productivity index, multiplied by P reservoir minus PB. And now this term here will go into a new form of Vogel equation, which actually uses QB. So QO equals QB, which is what's QB? QB is the flow rate at the flow bottom pressure equals bubble point. Okay, so QO equals QB plus J, which is the productivity index, times the flow bottom, so the bubble point pressure divided by 1.8, and then this is also multiplied by this term. And Qmax, if we want to know Qmax, so basically it's nothing but J times PR divided by 1.8. This is just an approximation. So again, if our test point is above a flow bottom pressure in the test is above the bubble point pressure, we use this equation here. Okay, find J, and then find QB, plug QB into this equation, and then we can construct our IPR curve. If the test is, the flow bottom pressure is below the bubble point pressure, it's a little bit different here. The only difference is that we cannot use J of the straight line. We use J from this equation here. But it's, again, it's just simple plugging just numbers, okay? So we have Q, the measured flow rate. We have the bubble point pressure. We have PWF. So we plug in this equation here, and we get one number, which is J. And again, we calculate QB using J. And then we use exactly the same equation here. Okay. Remember, from the reservoir pressure until the bubble point, it's a straight line, which means that since I know my test is just one line, and then from the bubble point pressure downwards, I'm going to use this equation here. So since I have J, so if my test is below the bubble point, I know J, so I go and calculate QB, and then I know PB, and basically I will just draw a straight line. And then I will continue using this equation here. Clear? And that's why we have now two more exercises. And I will leave these exercises here for you to practice, okay? And they will come in the quiz. But this is the exercise. Here what it says, and I put all the equations here just for your reference. So a well is produced from the reservoir with an average pressure of 4,000. If the flow rate was 2,000 and the flow bottom pressure was 3,000, the bubble point pressure is 2,000. Remember, this is a flow rate 2,000 and the bubble point pressure is 2,000. The reason I'm using these simple numbers is just for you to find the numbers, even numbers correctly. So now, as you can see here, the reservoir pressure is above the bubble point, which means we must construct two portions or two parts of the IPR curve. What we need to do, it's basically, remember, this is the flow bottom pressure, this is the flow rate, okay? And now the only thing is that we need to know what is, but we have to know, by the way, it's the same reservoir, because the bubble point pressure is 2,000. So not the same, it's a different reservoir. So the bubble point pressure is 2,000. This is the reservoir pressure. This is the flow rate, and this is the flow bottom pressure. How do you solve this equation? How do you construct the IPR curve using Vogel method? Number one, we calculate J. Again, I'm not going to solve this for you. I want you to practice. So J is what? J is nothing but dividing Q, which is 2,000, divided by P reservoir minus PWF. PWF was 3,000. The reservoir pressure was 4,000. So 2,000 divided by 4,000 minus 3,000, which is 1,000. So the 2,000 divided by 1,000, that's what? That's 2. So this is our PI. From PI, I can now get my QB. What is QB? QB is the flow rate at the bubble point pressure. At flow bottom pressure equals the bubble point pressure. So QB equals what? Equals J, which is 2, times P reservoir minus PB. P reservoir is 4,000. PB is 2,000. The difference is what? 2,000. 4,000 minus 2,000, that's 2,000. Multiplied by 2. Then what is QB? 2 times 2,000 is 4. So QB is 4,000. So I have now, excellent, Gulnar. I have 2,000 and 4,000. Okay. And now that's it. I have QB, which is 4,000. I have J, which is 2. And then I have my IPR curve. So I go and construct my IPR curve. I have to assume multiple PWF values, starting from P reservoir until 0. And then simply I create in Excel, I create a table, Q versus PWF, and then I can construct my IPR curve. Is that clear? Qmax is found from this equation here. So multiply J, which is 2 times P reservoir, which is 4,000, divided by 1.8. Okay, so this is Qmax. Because remember, this is not the same Vogel equation in which it's just saturated. As from saturated reservoir, we can use the original form, correct? So for saturated reservoir, we were using this one here. And here we can easily find Qmax. For undersaturated reservoir, this is Qmax, okay? And Qmax is just going to be used to complete the curve, okay? Yeah, exactly, 4,444, okay? So this is the exercise number 2. And now, as you notice here, the flowing bottom wall pressure, the flowing bottom wall pressure, which is 3,000, which was higher than the bubble point pressure, correct? Now, exercise number 3, it says, another well from the same reservoir, which means that it has the same PI. Sorry, not has the same bubble point pressure, okay? Another well from the same reservoir produced at a flow rate of 5320 when the flow bottom pressure was 1200. Construct the IPR curve using Vogel method. The only difference between this test and the other test, or this well and the previous well, is that the test point is below the bubble point. So now the difference between this exercise and this exercise is in the way we calculate J. So now, how do I calculate J for the second one? I simply go and say J equals QO, which is 5320, divided by P reservoir, which is 4,000, minus PB, which is 2,000, and then I continue, and then I will find J. Then I go and plug in, I calculate QB, and then I can construct my upper curve. It's exactly the same method, right? The only difference is that we have a different test. And then this is just for cheating purposes. You'll probably find that J is also 2. So I'm just verify that, okay? It's the same well. I just used a different test point just for you to practice. So eventually I will have the same IPR curve, correct? Great. Let's move on. How are we doing with time? What time is it now? To check. Yeah, we are doing good, I think. Oh, we're not doing good. We have only 12 minutes. Okay, let me continue quickly. Okay. Now, standing method. So standing is a famous scientist. You'll find standing correlations and in fluid PVT, in black oil PVT properties, standing method, right? So what did standing do? So standing said that the Vogel equation does not take into consideration the concept of skin, okay? So what he did, he went and evaluated a new concept on Vogel equation called flow efficiency, okay? So just quickly, what is the skin? So the skin is just a term that will represent the additional pressure drop that's close to the wellbore, okay? And this is mainly due to the damage that we do during drilling. When we drill, of course, we inject, mud and so on, and water-based mud to take the cuttings and to cool down the reservoir and to cool down the bed to work as lubrication, etc. But there will be some invasion from these fluids to the completion. We can create what we call mud cake, for example. Okay, so this damage will result in what we call skin. Again, skin is nothing but a term that represents this additional pressure drop. So scientists start to evaluate this term, and then they found that, okay, what if we manage to actually make this pressure drop around the wellbore is even less than the pressure drop in the reservoir? Then it's becoming a good thing, right? This is what we do in the stimulation or hydraulic fracturing, okay? Then it becomes a negative skin. What is the negative skin? Is this green line. So this straight line on the log, distance, if there is no skin, for zero skin, it will continue, right? The straight line will continue until we reach BWF. But of course, normally we have a skin. So the positive skin is when we have damage around the wheel bore. So that's why the slope of the pressure drop will start to go down, which means we are going to have additional pressure drop. So the flow bottle pressure will become less. But if we have stimulation, or if we have, let's say, better or less drawdown, then the rate of pressure drop will become less, and that's why we will have what we call negative skin. So let me just skip this. The only thing I want you to focus on is, again, what Standing did is that he considered this skin and looked into flow bottom pressure with and without skin, and then he came up with a new concept called flow efficiency. So what's the flow efficiency? Flow efficiency is the ideal drawdown divided by the actual drawdown. Ideal drawdown is this one here. This is ideal drawdown. Actual drawdown is this or this, okay? So if the actual drawdown, or let's put it this way, if the drawdown is going, the slope is going positive a little bit, that means the flow efficiency becomes positive, becomes more than 1, because the actual drawdown is less than the ideal drawdown, okay? And on the other hand, if we have damage, then the actual drawdown is less than the ideal drawdown, which means that the flow efficiency will become negative. So this is what Standing did. So then he came up with this concept, and then without going into so much details, this is the new equation that Standing did. You notice that it has almost the same concept of the of Vogel, right? But with some modifications. So this is the equation, right? So now, what are we showing here? We're saying that Q, okay. Just a second. No, I think this equation is not correct. I have to fix this. I'll fix it in next session. I'm really sorry for that. I think it's missing something here, right? Because it has to be an equation here, right? But anyways, basically we use the flow efficiency, right, and plug it into this equation here, which is nothing but a Vogel form, and then we are going to construct the IPR curve. Okay, so this exercise I will skip now until next time, where I'm going to fix this equation, and I'm going to show you how we are going to solve this. Again, next time I'm going to solve this, and it will become part of the quiz, possibly, huh? Okay. So let's move on. So Standing, again, I'm going to skip now. Okay. IPR methods for gas well, right? Remember in the beginning when I talked about PI, and I said for gas wells, we can say that Q equals J divided by P reservoir square minus PWF square, where this is not very, I would say, reliable. And the best way is to use what we call Vitkovich method. So Vitkovich method requires that you are going to have multiple tests, 3 or 4, okay? And then what do? We come up with a log-log scale. And then on the y-axis, instead of P reservoir, we are going to say P reservoir squared minus PWF squared, okay? And then to the power minus 6. Multiply to the power minus 6. And then this will be on the y-axis. Again, this is log scale. On the x-axis, okay, it's going to be Q, right? So now, what are we going to do? We are going to plot Q versus, you know, P reservoir pressure minus PWF pressure, okay? And then we will find that and we'll try to find a straight line that will fit all these tests, all right? And then from this curve here, we are going to find two important parameters. Number one, if I, you know, extend this straight line until 1, which is basically where PWF equals P reservoir, because this is log 0, then this is going to be C value, okay? And then when I extend this into the maximum, where this term here equals the reservoir pressure, then sorry, flowing bottom pressure of 0, which means that this becomes P reservoir pressure square, then I can get the absolute open flow. The slope of this straight line is N, right? So now, this is the equation. This is what we are going to use to construct our IPR curve from Fitkovich multi-rate test. So we have C, which is the flow coefficient. C is found from extending the straight line until the value of 1, P reservoir square minus PWF square. N is exponent that depends on the flow turbulence that varies between 0.5 and 1. And the log plot of P reservoir square minus PWF square versus Q gives a straight line with a slope of 1 point N. So the slope of this line is 1 point N, and intercept of C at P reservoir square minus PWF square equals 1. So this is how we get C, this is how we get N, and then we just plug in this equation here, assume multiple PWFs, we get Q, we can construct our IPR curve. Okay? And this is what you see, for example, in most of the similar, will performance software, whether it's Pipesym or Prosper, you will find that the back pressure equation is available where you enter C and N. This is the mostly used equation, okay? IPR methods for horizontal wells. So for horizontal wells, why we drill horizontal wells? Well, horizontal wells have been found to be very effective in the last 30, 40 years, okay? Why? Because the convergence is not going into a small area anymore, right? You can extend your completion, right, into a bigger area, and then the flow can easily and slowly move to that horizontal section. So there is lower tendency of water and gas coning. Okay, why? Because again, there is no localized area where the flow bottom pressure is less, and then this will invite oil and gas, water and gas coning, and then we can have it for high production rates. Okay, it is for the IPR method, it's best accomplished numerically. Okay, again by testing, right? But there are several analytical methods. And we're going to talk about, So we have two main classes or two main methods. It's either steady state method or pseudo steady state method, okay? So Joshi invented the famous Joshi equation, which is a steady state method, okay? What do we mean by steady state method? So steady state method assumes that the reservoir pressure at the boundary of the drainage area is constant, is steady state, okay? And basically he assumed, of course, there are some assumptions. So he assumed a constant, box, right? And then using some kind of geometry, he came up with this equation. So I will just read this equation and go to the terms. Okay, so Q equals 0.00708 times KH. So K, this is the horizontal permeability, times H, which is the height of the reservoir. PE is the reservoir pressure at the boundary minus PWF, okay, divided by, of course, mu B, which is the viscosity formation volume factor, times ln, and then we find that new terms A and I for anisotropy. So A is what? A is calculated from this term here. L is the reservoir, the horizontal length, right? So I know RE, I know the radius of the completion of the drainage area, sorry. So now from this equation here, I can come up with A, plug A into this equation. L again is the length of the horizontal section, right? I is given by this equation here, which is KH divided by KV. KH is the horizontal permeability, KV is the vertical permeability, okay? So square root of horizontal permeability divided by vertical permeability will give us the anisotropy, right? And then everything else is available. And then this is considering the skin. So the skin can also be either entered or calculated numerically. There are other equations to calculate the skin. So this is the Joshi IPR method, okay? And then there are some, this skin actually was modified by Economides at 1991, right? And this is basically the final form after modification, okay? The second type is Babwanodi, which is considered pseudo-steady state. Pseudo-steady state assumes that the whole reservoir drainage is constant, not at the edge, okay? So this is the equation, all right? We assume that a box like this, where we have the height, the width, and the length of the reservoir and the width of the reservoir, and this is basically so this is B, which is the width. A is this has to be not capital, it has to be small, and that's it. So CH is the shape factor, okay, that can be assumed depending on the drainage area, because this can be a different they call it dot shape factor, for example. And SR, the partial penetration skin, okay. This also can be either assumed or calculated, and there are also other equations to calculate the partial penetration skin, right? KY is the permeability on the Y direction. KZ is the vertical permeability, okay? And of course, B is the average reservoir pressure. I guess that's it for today. We're almost on time. Now